Our next speaker is Manki Kim from Cornell, who's going to tell us about Conifold Vacua with small flux superpotential. Take it away, Manki.
Thanks, Cody. And I'd like to thank first Cody and John for inviting me to give a talk on my research. Today, I'll talk about Conifold Vacua with small flux superpotential, which is based on the paper that will appear tonight on arXiv. Let me say a few words. We all know that our universe is expanding at an accelerating rate. But for some reasons, we still do not know if string theory is compatible with our universe. We all know that this is a big serious problem, and we should fix it once and for all. In order to approach this problem, I'm going to mostly talk about digital solutions in string theory, but note that there could be some alternatives, like quintessence. Okay, now I want to ask, where is digital hiding in string theory? Here I'm showing you a rough sketch of the moduli space of string theory. And over the past few years, we have gained quite a good deal of evidences that at least it is highly challenging to realize digital solution at strict infinite distance limits. However, we should not just conclude that there is no digital solutions in string theory, because by doing so, we're going to miss out the bulk of possibilities that string theory has to offer. Of course, if you want to go there, we may not have the perfect control over the theory, and we might need to get our hands dirty. Nevertheless, we should try hard. I think the very valuable first step in this direction is KKLT and its variants. So let me just talk about KKLT from now on. So what do you need to have KKLT in an explicit manner? What you want to have is first a string compactification, and given that compactification, you want to have the following modules. First, you want to have exponentially small W0, which is the value of the flux superpotential, and you may want to have at least one of the complex structure modulus that is stabilized near Conifold points. And you also want to have many rigid divisors to support non-perturbative superpotentials, and then at the last time, you may want to have a reliable SUSY breaking source to unlift. As of now, each of these modules is rather well understood separately if they are in isolation from each other. So what we must now do is to try to combine them in a given compactification. In this talk, I'm going to try to combine those first two by giving you an explicit examples. Note that I'm going to work in no-scale supergravity, and there are some criticism on this approach. Okay, so what's the goal? In this talk, I'm going to present to you the following results. First, I want to present how to compute a prepotential near Conifold points. And then I want to move on to find the mechanism to find small W0 near Conifold points. As a bonus, I'm going to also show you how to find Orientifolds for some Calabi-Yaos with many Kähler moduli. Okay, now that we have set the goal, let me review what's known before. Oh, by the way, see also a very nice work of Blumenhagen, Alvarez Garcia, and Brinkman and Schlechter on this same problem, which will appear tonight on arXiv simultaneously with ours. So let us review type 2B construction. First, consider type 2B superstring theory on a Calabi-Yau threefold, and I mean the Orientifold with O3 and O7 planes. Then what we know is that the no scale for the supergravity is described by the flux superpotential and the Kähler potential. The flux superpotential then induces potential on the complex structure moduli and axial delta modulus. So as a result of that, the complex structure moduli will adjust the VAV dynamically, and you can determine its VAV at the minimum. So if you want to construct Flux Vacua, the game you want to play is to pick the flux factors f and h such that the VAV of the stabilized complex structure moduli will feature the desired properties that you might want to have. For example, in this talk, I demand to have small W0 and at least one of the complex structure modulus should be near the conifolds. Now it is quite clear that we want to compute the flux superpotential to really know where the complex structure moduli are stabilized. In order to compute the flux superpotential, you need to know how to compute the integration of omega over some real 3 cycle. And we all know that computing real 3 cycles volume in a Calabi-Yau is a very challenging problem, unless you have the help of mirror symmetry. So mirror symmetry basically relates the volume of 3 cycles at the large complex structure with the volume of holomorphic even cycles in the mirror Calabi-Yau. So you can see that there is a table which summarizes which quantity is related to which, and you can see that the mirror map can compute the non-perturbative corrections to the volume of holomorphic cycles in the mirror. The nice thing about this way of packaging volumes is that you can efficiently write down all the volumes in terms of period pi or the prepotential and the flat coordinate z's. Okay, now that we know how to compute the period factor at the large complex structure, then now we can ask what is the structure that does the period have, and could we find some moduli not therein. So let us first look at the LCS prepotential. The prepotential at LCS has a very appealing feature, which is that the prepotential splits into the cubics and into the instanton terms. Especially the instanton contributions to the prepotential can be efficiently written in terms of Vacua invariance and trilogarithm, depending on the volume of mirror cycles. The thing that you want to remember is that Vacua invariance count the number of the two-brane BPS states wrapped on the holomorphic 2 cycles in the mirror. So given that splitting structure, we also know that we could also guess that the flux superpotential enjoys the same splitting into the cubic terms and into the instanton terms. And now we ask, is it really possible to find some moduli not? The answer is yes, and the trickery that we used in our last paper in December was that you can choose fluxes f and h such that there exists a perturbative moduli space in which the cubic terms, the leading terms in the flux superpotential vanish exactly. Then you can integrate out some of the heavy moduli, and there are going to be some light moduli, and those light moduli will be stabilized by the instanton corrections to the flux superpotential by realizing the racetrack scenario in an explicit manner. So let me give you an algorithm of this sort. So let Kijk be the intersection numbers of the mirror Calabi-Yau X. Then you can define vectors m and k and define a vector p, such that the vector p is in the Calican of the mirror Calabi-Yau and at the same time orthogonal to the vector k. Then in our paper in December, we gave you a way to construct the flux vectors f and h, such that, as I promised before, indeed the cubic terms in the flux superpotential is vanishing along a flat valley, which is parametrized by axial dilaton. So as you can see, the axial dilaton have no mass at this level, but that's fine because the axial dilaton will be stabilized by the type 2a Walsh instanton corrections to the flux superpotential. As you can see, the flux superpotential effective one has a racetrack-like structure. And the nice thing about this superpotential is that you can determine A and P's explicitly if you know the Vacua invariance and flux factors and Kijk. In case there is a nice preferable hierarchies between the prefactors, you can actually show that the flux superpotential VAV is exponentially suppressed. At the same time, the string coupling is stabilized at the weak coupling. As a proof of concept, we gave an example with the W naught roughly 10 to the minus 8 in our second favorite Calabi-Yau 1169. Okay, now that we have done the review, we must ask, how are we going to generalize this to the conifold points? Let me first briefly remind ourselves of what we know about the conifold points. I'm going to just assume that there is one conifold modulus, which will be identified as ZCF, and then let me just take the derivative of the prepotential in ZCF. Then what we know is that there is a term in the prepotential that looks like number of conifold NCF times the conifold modulus ZCF and times log of the conifold modulus. And in general, there is going to be a holomorphic piece that depends on all the complex structure moduli. And the point that I want to emphasize is that that holomorphic piece is not something that is highly suppressed. Rather, it is an order 1 contribution to the prepotential. And let us write down the Flux Superpotential and then split that into the conifold contribution and the bulk contribution. And then let us focus more on the conifold contribution at the moment. As you can see, there is going to be a standard GKP like conifold flux superpotential, and then you can just write down the F-time equations for the conifold modulus to find where the conifold modulus is stabilized. And you can see that the conifold modulus is exponentially suppressed, which means that you're extremely close to the conifold point. As a reminder, the size of the tip of the throat, I mean the KS throat, is determined by GSM. So if you want to have a nice supergravity description near the conifold, near the tip of the conifold, then you might want to have large GSM. Anyhow, let us go back to the flux superpotential story. The thing is that if you stabilize conifold modulus extremely close to the conifold point, then you can mostly neglect this conifold-like terms, and then you can just focus on the holomorphic piece. But basically, as I said, the holomorphic piece to the conifold superpotential is order 1 thing. It's not suppressed. So in order to have small W naught near the conifold, the challenge for us is to compute the holomorphic piece F ZCF, Z as accurately as possible while retaining the structure of the LCS prepotential as much as possible, because we basically want to cancel the M times F against the bulk superpotential. So now it is rather quite clear that we want to compute the conifold period very accurately. So we presented a general method to compute the prepotential, but let me just give you a simple example. If you're curious, you can look at our paper appearing tonight. So I'm going to mostly work with a Calabier with H113 and H2199. The very appealing feature of this Calabier is as follows. So the diagram that you're seeing now is a 2D projection of the lattice of effective curves. And then you can see that there are some points that are marked with the colors. One of them is blue and the other one is red. And all those points that are marked with some color are the effective curves that have non-vanishing Gopakumov-alpha invariants. And you can also see that there is an interior cone in the lattice of effective curve, and there is one outlier, the red dot, which I'll call sigma 1. So now let us entertain the possibility of collapsing the volume of sigma 1 and ask what happens. As you collapse the volume of sigma 1, what you will see is that there is going to be n sigma 1, which is the Gopakumov-alpha invariant of sigma 1, worth of massless BPS states coming down as you collapse the volume of sigma 1. And we must ask, what is the mirror dual of that curve, of that singularity? And the natural guess you can make is that, well, as there is going to be only finite massless states coming down, it's probably going to be a conifold singularity. This is a very good speculation, and we actually showed by going through some long computation that indeed this is mirror dual to a conifold singularity in X tilde. So you can trust me at this moment, and then I'm going to just identify Z1, which is the volume of the collapsing curve, with the conifold modulus, and the Gopakumov-alpha invariant of sigma 1 with the number of conifold. The nice thing about this collapsing volume, is that you can determine the holomorphic piece of the conifold period in a very efficient manner and in a very simple manner by just resumming infinite instances. It's just all talk. Let me just give you a concrete way to do that. So at the large complex structure, the prepotential, as I said before, splits into two pieces. One is the cubic and one is the instanton pieces. And we know how to resum the cubic terms when we send z1 to 0. So let me just focus on the instanton terms. If you look at the instanton terms, then there is one contribution from the outlier curve whose volume is going to collapse. As you can see, there is a term like number of conifold times dilogarithm depending on the volume of the collapsing curve. And the bunch of instanton corrections to the prepotential from non-collapsing curves. Excuse me. And let us stare at this formula for a bit. Then you can possibly convince yourself that this expansion, LCS expansion, is even well behaving near z1 is equal to 0. Given that fact, what you can do is to use some resummation formula to expand the instanton prepotential near z1 is equal to 0. There is a very nice formula, so-called Euler reflection formula, so let me just use it. If you use the Euler reflection formula, then what you get is that the instanton piece of the conifold period has a term like number of conifold times conifold modulus times log of conifold modulus. So this is exactly what we were expecting to get. And you can actually see that we could efficiently determine the holomorphic piece of the conifold period by just expanding things around. This is all good. Now let us start studying the conifold flux superpotential. So as we want to stabilize conifold modulus extremely near to the conifold points, I'm going to work with the expansion scheme in which the conifold modulus is exponentially suppressed. Then you can see that the flux superpotential enjoys exactly the same structure that we had for the LCS superpotential, just because of the fact that we are going to have some cubic terms, and we are going to treat the conifold modulus and the other remaining instanton corrections as exponentially suppressed subnetting corrections. So we have retained most of the good structures of the LCS flux superpotential, and the now guess is that, well, then we might be able to use the same trickery that we used for the LCS case to find small W naught. And that is true. So the way that I'm going to do is to choose fluxes f and h such that there exists, again, a perturbative moduli space in which a little different change, the double cubic in the zeroth order of the conifold modulus, is vanishing. Then, as you can see, again, the remaining light moduli are present, but they are going to be stabilized by the subnetting instanton-like corrections to the flux superpotential, again realizing the racetrack-like scenario. Although it is almost repetition, let me just give you a method again. So let k be the intersection number of the Miró-Calabi-Yau X. Then you can again define vectors m and k and vector p such that the vector p is in the Kelarcon of the Miró-Calabi-Yau X, and at the same time p is orthogonal to k. Oops. Then in the similar way that we did for the LCS flux superpotential, you can also choose the flux vectors f and h such that indeed the zeroth order cubic term is vanishing along a flat valley, which is parametrized by axiodelaton. Now that we have two massless moduli, one is axiodelaton and the other one is conifold modulus. So we want to stabilize them, and let me write down the effective superpotential for them. The effective superpotential is just written as the standard GKP-like flux superpotential plus lots of instanton corrections depending on the axiodelaton. And one minor tweak that I want to emphasize is that in the standard GKP flux superpotential, there is no the flux mixing that is marked with the red color. There is only K1. The nice thing about this mixing between bulk flux and the conifold flux is that the presence of this flux will allow you to tune the conifold modulus by a lot while roughly fixing the value of W0. You will see that in the later slides, there are many degenerate solutions stuck at the same W0. Anyhow, you can solve F-term equations for the conifold modulus and the axial dilatome and compute the value of W0. The result is again that W0 is exponentially suppressed, and at the same time the conifold modulus is extremely close to the conifold point. Note that in the vacua that we're quite interested in, that could be used for the dizzy-term lifting, the value of the conifold modulus is set by the axial dilatome, and mass of the conifold modulus is a lot bigger than mass of axial dilatome. So now we have found a method to compute the prepotential and method to find W0, but we haven't yet fully resolved the problem because we do not know what the tadpole bound for the flux is. So to do that, let me find some Orientifold. There is one technicality, because the Calabi-Yau that we're interested in, X tilde, has many Keller moduli, and some of which are non-toric. Let me just give you the definition of what the toric is. We basically call the devices that are inherited from the ambient variety the toric devices. Nevertheless, it turned out that it is quite feasible thing to do to compute the H11 minus and H21 minus. So let me just do that. Let me first write down the defining equation for X tilde. The defining equation for X tilde is given as that, and there are many monomials and many coordinates, excuse me, sorry about that, but the only important coordinates are x2 and x8 and x9. And note that x8 and x9 will give you the non-toric devices. And the Orientifold action that I want to consider is a map that sends x2 to minus x2. As you can see from the defining equation for X tilde, only one of the monomials is projected out under the Orientifold action. And you can also easily compute that the dimension of the automorphism groups of the ambient variety that commutes with the Orientifold action is 4. So now you can count how many independent complex structure moduli there are. Let me just count it for you. There are in total 8 monomials that are projected in, and you know that there are 4 redundant ones because of the automorphism group, and we also know that the overall scaling of the defining equation doesn't really matter. So in the end, I get H21 minus is 3. And now let us compute H11 minus. What we know about this kind of Orientifold action is that this simple inversion doesn't really do much on the toric divisor classes. So we at least obtain H11 plus 97. Then the remaining task for us is to compute the Orientifold action on the non-toric devices. Let me give you an example. There is a non-toric divisor class, X8, and you can solve the equations, and then you will obtain the following result, that there are 2 distinctive copies, disconnected copies. So one of them is a non-toric divisor. And the nice thing is that the Orientifold action x2 goes to minus x2 acts trivially on those devices. And the same result is also true for x9. So what we obtain is that I tilde acts trivially on all of the devices, which means that H11 minus is 0. So now, in order to compute the D3 brane tadpole, we're going to place 47 branes on every single O7 plane. As a result of that, we can just use the Lefschetz fixed point theorem to compute the D3-ring tadpole band, which is 52. Because we didn't have enough time to tell you more about the exciting details of the Orientifold, I think I'm gonna just wrap it up at this point, but if you're curious, please look at our paper. So we now have all of the things that are needed to find Flux Vacua near the conifolds. So let me give you some statistics. So this plot contains the Flux Vacua with the tadpole smaller than or equal to 52, and some of the Flux Vacua contains GSM smaller than 1. And as I said before, GSM determines the size of the tip of the thread. So if GSM is smaller than 1, then the supergravity approximation may not be amazing. Anyhow, you can see that a very small value of W0 is indeed possible, and there is some freedom for you to choose or tune the conifold modulus. If you're curious about how many vectors there are that could be used for determ lifting, then let me present to you how many vectors there are. So basically, this red line indicates the line in which, if there are points on the line, the warped tension of some anti-D3 ring is roughly of order F10 potential. So you can see that it is indeed possible to have some fine-tuning such that the unlifting is possible. And if you're curious about the GSM larger than 1, here they are. Again, there are quite a good deal of vacuum. Okay, and let me give you some interesting vacuum that I fairly like. The minimum value, even with the very small tadpole, 52 is a very small tadpole. Even with that somewhat marginal tadpole, we were able to find W0, which is roughly 10 to the minus 9. Of course, because our tadpole band was relatively low, we were not really able to find very large GSM. So the maximum GSM that we were able to find was roughly 2.8. But it's not because our method is banned to find small GSM, rather we're just being lazy in finding good Orientifolds. I want to also emphasize that there are many vacua with GSM smaller than 1, and they are legit vacua. But they are quite less studied compared to the supergravity regime. So we may want to study what kind of Susy breaking is possible in KS gauge theory. So let me conclude. In this talk, in this work, we have found a method to find conifold prepotential and small W0 near the conifold points, and at the same time, as a bonus, a method to find Orientifolds with many Keller moduli. And as I emphasized before, we didn't do a very hard work in finding good Orientifolds and good conifolds, so we should do more extensive search. One feature of our method is that like complex structure moduli are inevitable. Then the thing is that if you want to do the Keller stabilization, we typically fix the Orientifold of the Keller non-perturbative superpotential to be some value. But unless we understand a lot about Orientifold, fixing the value of Orientifold may not be such a great idea. So we should also compute the Orientifold in a great detail to fully explicitly stabilize Keller moduli. And of course, the quest to find KKLT digital vacua in string theory must continue. Thank you.
All right, let's thank Manki for the excellent talk. Are there any questions? Well, while we wait for questions to roll in, so this was an example with relatively few complex structure moduli.
Yes.
Do you have any idea yet how the expected value of small W0 scales as a function of n and being the number of complex structure moduli?
Yeah, from the Denef and Douglas type argument, you can expect that the number of W naught, the value of W naught, roughly scales as tadpole to the -2 times number of moduli, or -4 times number of moduli. So if you increase the number of moduli, then you will see the smaller W naught.
And so from your studies, are you seeing that Denef Douglas approximation to be about correct?
In the case where we studied LCS, we were indeed finding that our result is compatible with Denef and Douglas type argument, but we didn't do that kind of study in this work. But that's a very important direction to study if Denef Douglas type argument is also working in the Conifold case.
Very cool. All right, are there any other questions for Manki? Irene has a question.
Hi, Manki. Thank
Hello.
you for the talk. It was very
Thanks.
nice. Yeah, just a quick thing. I'm not sure if you said it, but in the last slide, did you find any correlation between how small is W naught and how big can be GSM?
That's a very good
Because
question.
it seems that maybe
Yeah.
it's just a matter of this particular example. But I noticed that when W naught is very small, also GSM was smaller. And I wonder if there is any correlation.
That's a very good question. Given the preliminary study, we didn't see a high degree of correlation when we increased the tadpole bound to see more vacua. So I think this example has a very high degree of coincidence, but we still do not know if this correlation may really persist in many other different Calabios. So we should study more. Thank you.
All right, and Jakob has a comment.
Thank you. Irene, so for these vacua, we sort of chose the best vacua that we could find for different criteria. So for instance, the first one is the smallest W naught that we found in total. So GSM is something that just comes out as it is. So it's a bit deceiving because we chose smallest W naught, best value of GSM, for instance, and of course, when you enforce finding the best for one quantity, everything the other quantities will not be as great.
Mm-hmm. Okay.
So we don't have correlation.
Okay, if there are no more questions, let's thank both Manki and Craig again